In Chapter 4, we're talking about probabilities. These are going to be based on experiments or procedures. So some examples of experiments, things like rolling a die, flipping a coin, drawing 2 cards from a deck, or conducting a survey asking a person's gender in one yes or no question. Those would all be examples of experiments. Now, when we talk about outcomes, these are the possible things that can happen in each trial of an experiment. So each time you repeat the procedure, then you have a possible outcome. You have a set of possible outcomes. For example, if you're rolling a die, on each roll, your possible outcomes are to get a 1, 2, 3, 4, 5, or a 6. If you're flipping a coin, your possible outcome for each trial is either getting a head or a tail. If you're drawing 2 cards from a deck, here are just a couple of the possible outcomes. You could get an ace of spades and a 2 of hearts, for example, or you could get a 5 of clubs and a queen of hearts. There are lots of different possible outcomes for that particular procedure. And if you're conducting a survey, this is one that we run into a lot. If you're only asking the person's gender in one yes or no question, then here are the different possible outcomes for each response to the survey. It can either be male and yes, male and no, female and yes, or female and no. So in that one, there are actually 4 possible outcomes. Now, just some terminology. When we talk about an event, this is when we're repeating a procedure, so we have an experiment, and we have all those different possible outcomes that we just talked about. An event is any collection of outcomes. So it can be one single outcome, it can be several of the possible outcomes of an experiment, it can even actually be all of the possible outcomes of an experiment. So here's an example from our survey experiment, and we usually use capital letters to stand for events. So for example, event A could be that the respondent is male. Event B could be that the respondent answered yes to the question. Event D could be that the respondent is female and answered yes to the question. So these are just some different possibilities. Now, when we talk about a simple event, this is an outcome or an event that can't be broken down further into simpler components. An example of this would be in our experiment of rolling a die, rolling a 6. That can't be broken down any further. On the other hand, if we talked about rolling an even number, that could be possibly a 2, a 4, or a 6. So that wouldn't be a simple event because it could be broken down into smaller pieces. For the survey experiment, a simple event would be that the person was female and answered yes to the question. And finally, a sample space for an experiment is just a list of all the possible simple events. So it's a list of all the possible outcomes of the experiment, kind of like we were doing on the last page. Notation for probabilities. A capital P denotes a probability. Like I said, A, B, and C, capital letters usually denote specific events. And if you have P and then an event letter in parentheses, that means the probability of an event occurring. We have 2 different ways we can compute probabilities. The first way is what the book calls a relative frequency approximation. This is using data, observations from something that's already been done to approximate probabilities for something that's going to happen in the future. So this is using actual results to approximate probabilities. So if we've already run an experiment or conducted an experiment or observed a procedure, then the probability of a specific event would be the number of times that event actually occurred when we observed this experiment, divided by the number of times the procedure was repeated, or the number of trials in the experiment. Here's an example. Data was collected concerning head injuries to skiers. Out of skiers that had accidents and were not wearing helmets, 480 had head injuries and 2,330 did not. We can think of this as an experiment just by looking at the data that was collected. So if we randomly select a case where a skier had an accident and was not wearing a helmet, we're going to let A be the event that the skier had a head injury. So this is not that we're selecting a case from the data that we looked at. This is that we're selecting a case from all skiers that had accidents. But we're going to base the probability on the data that we already have. So we can approximate the probability of a skier having a head injury through an accident by using a relative frequency approximation from the data that we already have. So to get that, the probability from our data that the skier had a head injury would be the number that did have head injuries, so that's our 480, divided by the total number of accidents that we were looking at. And this is an important part. You have to add the ones that had head injuries and the ones that didn't to get your total. So on the bottom we have 480 plus 2,330. So our probability is the 480 divided by the 2810, which is approximately 0.1708. And kind of a rule of thumb here is that we're going to round to 4 decimal places. Now if we wanted to write this as a percentage, again, here's where we deal with our percentages. We move our decimal point 2 places over to the right, so we get 17.08%. Now another way to compute probabilities, the book calls this the classical approach. Sometimes you'll see me calling it the theoretical approach or the theoretical probability. This is if we have a certain number of simple events in our sample space. So if we count all the outcomes in our sample space, and if we know that each one of those has an equal chance of occurring, then for each one of those in the sample space, the probability of it is 1 divided by n. Or another way we can think about it is that if we have a specific event, if it can occur in s different ways out of the n, then the probability is just going to be s over n. So in other words, it's the number of ways our event can occur divided by the number of different simple events, or the number in the sample space. Here's an example. If a bag of M&Ms contains 30 blue, 25 brown, 16 yellow, 12 red, and 20 green candies, find the probability that a candy randomly selected from the bag is red. So the event that we're looking at is that the candy is red. So let's call that A. And here's where we're doing our theoretical probabilities. We look at how many different ways we could select a red candy from the bag. Since there are 12 red candies in the bag, then we could do that 12 different ways. And the total number of events in our sample space altogether is the total number of candies in the bag. So we're just adding the numbers from the different colors to get 103. So the probability of selecting a red candy, that's the probability of our event A, is going to be 12 divided by 103. If we round this to 4 decimal places, we get 0.1165. If we want to convert that to a percentage form, that's 11.65%. Now when we talk about probabilities, there are only certain values that can be a probability. We can't have negative numbers. A probability cannot be greater than 1. And if we're talking about a probability in percentages, that would be 100%. So it can't be greater than 1. It can't be greater than 100% if we're talking about it in terms of percentages. And 1 or 100% means that the event is certain to happen. That's the only thing that can happen. 0 means that, or 0% means that it's impossible, that there's no way that it can happen. Now, complementary events, when we talk about the complement of an event, in this book they use a line over the event to denote the complement. This is just, it's kind of like the opposite of the event. It's all the outcomes where the event doesn't occur. So an example would be with our bag of M&Ms, we said that A was the event that the candy that we select is red, so the complement of A would just be the opposite of that, that the candy is not red. And here are a few rules for complementary events. These all involve the probabilities. Number one, if we add the probability of an event and the probability of its complement, we have to get 1 because they're exact opposites of each other. This gives us a way to find the probability of the complement. We just subtract the probability of the original event from 1. And also, if we already know the probability of the complement, we can get the probability of the event by subtracting from 1. So here's an example with our M&Ms. We already know that the probability of A, that was that the M&M was red, is 12 over 103, or 0.1165. So if we wanted the probability of the complement, that the candy is not red, we would just take 1 minus the probability of our original event. This would be either 1 minus 12 over 103, which would give us 91 over 103, or we could do it with the decimal values, which would be 1 minus 0.1165, and that would give us 0.8835. Either way, we get the same answer. And here's a Venn diagram that just illustrates complements a little bit. This whole box is our sample space. So the box is our sample space, which is all possible outcomes. And what we're saying is that the yellow part in here is our event, our original event A, and so we've got the probability in there. Everything that's outside that circle is the complement of A. So, and we want the total area of the box to be 1, so that means that what's in the circle and what's outside of the circle have to add up to 1. Now when we talk about a compound event, this is just any event that combines 2 or more simple events. For example, if we have the probability of A or B, this would be the probability that either event A occurs or event B occurs, or they both occur in a single event. And the general rule for a compound event, and this is when we're talking about the probability of, say, A or B, we want to find the total number of ways that A or B can occur, but we have to do that so that we don't count anything twice. Here's an example. This goes back to our head injuries with skiers, but this time we have a little bit more information. Out of the skiers that had accidents and weren't wearing helmets, 480 had head injuries, 2,330 did not. Out of skiers that had accidents and were wearing helmets, 96 had head injuries and 656 did not. So what if we want to find the probability that a randomly selected skier that had an accident either wore a helmet or did have a head injury? This would be a compound event. So first, it's really easy if we put the information into a table. So I made a little table here. We've got head injury or no head injury, no helmet or helmet. So our first piece of information up here goes into the no helmet column. So we had 480 with head injuries, 2,330 without. And then we have the ones that were wearing helmets, so those go into our second column. So we had 96 head injuries, 656 without. Now to find our probability, what we want to do is add up all the cells either where the skier was wearing a helmet, which would be these two, and we also need to put in the ones where there was a head injury. So we've got the 480 and the 96 where there was a head injury. We said that we didn't want to count anything twice. This 96 actually comes in to both categories, but we can only count it once to get the correct answer. So we're just going to add up these 3 cells. So our 480, our 96, and our 656. That adds up to 1,232. And the total in the table is what is going to have to go on the bottom of our fraction. So if we add up all 4 values, we get 3,652. So our probability is 1,232 divided by 3,652, which is approximately 0.3373. If we want to put this into decimal form, it's 33.73%. Now, one more kind of probability is conditional probability. This means that we already know something about what's occurred. We're assuming that one event has already occurred, and we're finding the probability in that case that another event occurs. And this gets a little confusing because we're really talking about conditional probabilities, but we call this the multiplication rule. What this means is if we're talking about the probability that A and B both occur at the same time, so two different events that have some kind of overlap, for example, having a head injury and wearing a helmet, those could overlap. So the probability of both of those happening at the same time is the probability of the first one times the probability of the second one given the first one. That seems really confusing. What we're really going to use this for is for our conditional probabilities. This is the one that we're really looking at. The probability of B given A is equal to the probability of A and B. A and B is the same as intersection, divided by the probability of A. And notice that this one, the one that you're dividing by here, has to be the second one in your conditional probability. Okay, and finally, if A and B are independent, which means they don't affect each other, then P of B given A is really the same as P of B. So in that case, our multiplication rule up here actually helps us, and that says that the probability of A and B is just the probability, the two probabilities multiplied together. Okay, let's look at an example. So back to our skiing example. If we want to find the probability that a skier was wearing a helmet given that they had a head injury. So this is a conditional probability because we've got something that's given. So let's use H to stand for the event that the skier was wearing a helmet. Let's let I be the event that there was a head injury. So what we're trying to find is P of H given I. Here's our formula. P of H given I is P of H and I divided by P of I. Well, H and I would be that they were wearing a helmet and that they did have a head injury. So if we look at our table, where the helmet and the head injury intersect is right here with the 96. So our probability for that would be 96 over the total that was in the table, which was 3,652. Here's the decimal approximation, and notice that I took this out to as many decimal places as I could. It's dangerous to round here. It tends to lead to rounding errors. So I took this out to 6 decimal places. Then with P of I, that's just the probability that they did have a head injury. So for that one, we want to look at all the head injuries in this table, which would be the 480 plus the 96, and then divide that by our total. So that gives us approximately 0.157722. Then for our final answer, our conditional probability, we just divide those two and we get 0.1667. All right, so a summary of what we've been talking about. When we talked about the addition rule, we had the word or when we were saying P of A or B. This suggests addition. So we're adding different cells in the table together. But we have to be very careful so that every outcome is only counted once. When we had the multiplication rule, there we were using the word and that kind of goes with multiplication. We can multiply the probabilities, but we have to make sure and include that conditional probability in there.